Humanity's next home might not be a country, but an entire solar system. Our future among the stars depends on colossal engineering feats that redefine the possible. In this exploration, we will uncover 20 interplanetary megaprojects designed to rebuild civilization beyond Earth. You will discover the foundational blueprints for everything from orbital cities to transformed planets. How could we engineer a breathable atmosphere on a dead world? And what kind of society would choose to live inside a giant, rotating cylinder in the void? These endeavors challenge us to ask not only if we can achieve them, but what we become in the process. Which of these stellar ambitions feels most urgent to you? The red deserts of Mars could one day be painted green. This vision for a transformed planet begins with the Martian Terraforming Initiative, a master plan to re-engineer an entire world. The first step involves placing vast orbital mirrors, each larger than any city, to focus sunlight onto the polar ice caps. This concentrated energy would slowly melt the frozen carbon dioxide and water, releasing thick clouds of gas into the thin atmosphere. As this blanket of carbon dioxide thickens, it traps solar heat in a powerful greenhouse effect, warming the planet by dozens of degrees over many decades. This artificial spring would unlock frozen water, creating streams and shallow seas under a pinkish sky. Yet an atmosphere you can breathe requires more than warmth, it needs oxygen. That is where the second phase begins, introducing specially engineered microbes into the new Martian soil and water. These tiny life forms would be designed to thrive in the harsh conditions, slowly consuming the carbon dioxide and releasing breathable oxygen as a byproduct, a process that could take centuries to complete. Experts like planetary scientist Chris McKay suggest that while the timeline is immense, spanning generations, the outcome is a second habitable world for humanity. This endeavor is not just engineering, it is the ultimate act of planetary stewardship. It forces us to consider the ethics of creating an entire biosphere from scratch. What responsibilities do we have to any potential native life, even microbial, and how do we design an ecosystem that remains stable for millennia? The ambition to terraform Mars is more than a technical challenge. It is a profound statement about our species' future, paving the way for even grander acts of cosmic creation. While the surface of Venus is a crushing inferno, a world away exists just 50 kilometers above. Here, in the upper atmosphere, the temperature and pressure are almost identical to those on Earth. This is the proposed home for the Venus Cloud City Archipelago, a fleet of vast floating metropolises. These would not be rigid structures fighting the elements, but graceful platforms designed to float permanently in the thick air like buoyant islands in a yellow sky. Constructed from ultra-lightweight aerogels and carbon composites, each city would essentially be a giant, sealed envelope filled with a breathable atmosphere. Since our air is lighter than the dense carbon dioxide of the Venusian atmosphere, these habitats would naturally float, requiring no energy to maintain their altitude. Aerospace researcher Jeffrey Landis has long championed this concept as a more immediate and less resource-intensive path to colonizing another world. The archipelago would be a self-sustaining network, harvesting the abundant carbon dioxide from the air to produce breathable oxygen and even manufacture rocket fuel, turning the planet's greatest challenge into its primary resource. This vision does not attempt to conquer a hostile world, but to adapt to it, demonstrating a form of engineering that works in harmony with alien environments. It turns a seemingly hellish planet into a breathtaking haven, proving that our future in the stars may not always be about remaking worlds, but learning to live within them as they are. These stable points in space, where the gravitational pull of Earth and the Moon cancel each other out, offer a perfect anchor for the solar system's greatest industrial endeavor. The Lagrange point orbital shipyards would be more than a factory. They would be a cradle for giants, freed from the crushing grip of a planetary gravity well and the thick blanket of an atmosphere. Engineers could construct vessels on a scale previously confined to science fiction. Picture a framework of girders stretching for kilometers, bustling with robotic arms and suited workers, all focused on assembling a starship's hull piece by piece. The raw materials for this colossal undertaking would not be hauled up from Earth at great expense, but delivered from nearby asteroids, rich in metals and minerals. In the gentle embrace of microgravity, massive components can be moved and welded into place with minimal effort, allowing for the creation of ships with vast rotating habitats for artificial gravity and engines powerful enough to push them across the void between stars. This centralized hub for spacecraft manufacturing would fundamentally change our relationship with space. By building our exploration fleet in orbit, we avoid the tremendous fuel cost and engineering challenges of launching a fully assembled interstellar ark from a planet's surface. This single innovation could slash the economic barrier to deep space travel, turning a once-in-a-generation voyage into a regular occurrence. These shipyards represent the moment a space program evolves into a spacefaring civilization, an economy built among the stars. But such an immense industrial complex requires an equally immense source of power to operate, a demand that leads us to the next megaproject. To power such a civilization, we must turn to the ultimate engine of our solar system. The Sun radiates more energy in a single second than humanity has used throughout its entire history. A Dyson Swarm proposes capturing this immense power not with a single solid shell, but with a vast, coordinated cloud of individual solar collectors, each one a habitat or a power station in its own right. These millions of satellites would form a loose sphere around our star, continuously harvesting its light. This energy would not be wasted, it would be transmitted across the void. Using precisely aimed lasers or low-intensity microwaves, these harvesters could beam power to a receiving station on Mars, a cloud city above Venus, or the orbital shipyards at Lagrange Point, providing a clean and nearly limitless source of electricity for every corner of our interplanetary society. This concept, inspired by physicist Freeman Dyson, is less about building a rigid structure and more about orchestrating a celestial dance of energy collection on an unimaginable scale. Constructing such a swarm would require a workforce of billions, but not a human one. The only practical method would be to deploy self-replicating robotic factories. Picture a single automated craft landing on a mineral-rich asteroid. It would use the raw materials on site to build 2 copies of itself, which would then fly to 2 new asteroids and repeat the process. This exponential growth would quickly create an army of autonomous workers, capable of processing entire worlds into the solar panels and satellites needed for the swarm. This represents a technological tipping point, a moment when our tools become capable of not just assisting us, but of physically rebuilding the solar system according to our design. With a total energy output of a star at our command, what could we achieve? We could accelerate the slow process of terraforming a planet by centuries. We could power supercomputers that model entire climates or simulate complex new materials. We could ultimately support a society free from the struggle for resources, a true post-scarcity civilization where energy is as abundant and available as sunlight on a clear day. This network would form the fundamental power grid for all our other ambitions, allowing us to truly begin the work of reshaping not just worlds, but our own cosmic destiny. Deep within the asteroid belt, a small world holds the key to feeding a civilization. Ceres, a dwarf planet rich in water ice, is the proposed site for hydroponic arcologies, city-sized biospheres sealed under vast domes. These are not mere greenhouses, but self-contained ecosystems designed to produce food on an industrial scale for millions of people living across the inner solar system. The core of each arcology is its hydroponic farm, a multi-layered labyrinth where crops grow not in soil, but in nutrient-rich water, bathed in the precise spectrum of artificial light. This method uses a fraction of the water required by traditional agriculture and allows for year-round harvests, completely independent of the hostile environment outside. But the vision extends beyond pure utility. The architects of these arcologies understand that long-term survival in space depends on more than calories. It requires a connection to life itself. The interiors would be carefully crafted to mimic Earth's most comforting landscapes, with parks, forests, and flowing streams under a simulated sky. This provides vital psychological relief from the stark blackness of space, offering a living reminder of the world we came from. By turning Ceres into the central breadbasket, we would solve one of the most fundamental challenges of a spacefaring society: the logistics of feeding a population dispersed across millions of kilometers. This security allows other colonies to specialize, focusing on mining, research, or manufacturing, knowing their sustenance is guaranteed. A civilization that has mastered its food supply is free to build, but to build, it needs materials. This need draws our attention to the resource-rich asteroids themselves. The vast distances between worlds are not empty voids, but a landscape of invisible pathways. This is the Interplanetary Transport Network, a solar system highway built not from asphalt, but from the subtle curves of gravity itself. These are low-energy orbits, pathways where a spacecraft can coast with minimal fuel, guided by the gravitational pull of planets and moons. It is a cosmic version of catching a current in the ocean, letting the natural forces of the solar system do most of the work. To make this system truly practical, we would need to build infrastructure along these routes. Picture refueling depots stationed at strategic points, allowing ships to top up their tanks without returning to a planet. Imagine waystation habitats where travelers can rest, repair their vessels, and transfer cargo, creating bustling interplanetary ports in the deep silence of space. This network would transform spaceflight from a series of daring, isolated missions into a routine and efficient flow of commerce and culture. It becomes the circulatory system for a living, breathing civilization spread across multiple worlds, with resources and people moving as reliably as trucks on a terrestrial highway. This constant, reliable flow is the essential backbone that supports our next great ambition: unlocking the almost unimaginable material wealth of the asteroid belt. The asteroid belt is a treasure chest waiting to be opened, holding more mineral wealth than our entire planet could ever provide. This is the domain of the Asteroid Belt Mining Consortium, a future enterprise where fleets of autonomous drones would work in perfect coordination. These are not simple robots, but sophisticated machines capable of identifying, landing on, and systematically extracting value from the millions of asteroids drifting between Mars and Jupiter. Their targets would be the precious metals like platinum and gold, vast deposits of water ice locked within the rock, and rare minerals essential for advanced electronics. Once harvested, these raw materials would not be sent back to Earth in their crude form. Instead, they would be processed at local refineries right there in the belt, turning raw ore into pure ingots of metal and blocks of water ice ready for transport. This constant stream of resources would then flow along the interplanetary transport network, feeding the orbital shipyards and construction sites across the solar system. Every new spaceship hull, every microchip for a cloud city's computer, and every panel for a Dyson Swarm satellite would find its origin in these dark, rocky bodies. This enterprise would effectively end our dependence on Earth's finite and dwindling reserves, launching an economic and technological boom of unprecedented scale. The capital generated from selling these materials would fund even more ambitious projects, creating a self-reinforcing cycle of growth and expansion. But these metals and minerals are not just for industry, they are the very bones of future homes. The resources mined here will be absolutely essential for constructing the permanent, self-sustaining habitats where millions will live, work, and build new lives far from our home world. Freedom from a planetary surface means creating entire worlds from raw materials and imagination. The O'Neill cylinder habitats are precisely that, vast cylinders spinning silently in the void, each one an engineered paradise built from the metals and minerals of the asteroid belt. Proposed by physicist Gerard K. O'Neill, each cylinder would be miles long and wide enough to contain rolling hills, rivers, and even small towns under a glass ceiling that runs the length of the structure. The spin creates an outward force that mimics gravity, pulling everything toward the inner curved surface, allowing soil to stay in place and trees to grow upward. You could stand on a grassy field and look up to see other landscapes suspended overhead, with clouds forming naturally from the carefully managed atmosphere and water cycle. This is not merely a space station, it is a fully realized, self-regulating biosphere capable of supporting millions of people with its own agriculture and weather. The ultimate engineering challenge lies in achieving a perfect, stable balance between all the biological and mechanical systems, ensuring that the air remains fresh, the water pure, and the soil fertile for generations. These cylinders demonstrate that we are not limited to the world's nature provides. We can build our own, tailoring the environment to our exact needs and placing these island homes in stable orbits around the Sun, far from the gravitational wells of planets. This represents a profound shift in human existence, the ability to live comfortably and sustainably almost anywhere in the solar system, carrying our own little pieces of Earth with us into the cosmos. Beneath the frozen, fractured crust of Jupiter's moon Europa lies an ocean. This is not a metaphor, but a real body of liquid water, containing more than twice the volume of all the seas on Earth, sealed under a shell of ice miles thick. Reaching it is one of the greatest engineering puzzles in the solar system. The proposed solution is a nuclear-powered cryobot, a self-contained probe that would use the heat from a small reactor to melt its way straight down, descending slowly through the ancient ice. This journey through the frozen darkness could take a year or more, a lonely pilgrimage into the abyss. Upon finally breaking through, the cryobot would become a gateway, releasing a fleet of autonomous submersibles into the alien sea. These drones, built to withstand immense pressure and complete darkness, would be our eyes and hands in this unexplored world. Their primary mission would be to search for biosignatures, chemical traces that hint at the presence of life, whether past or present. Finding even the simplest microbial organisms here would be a discovery of epoch-making importance, proving that life is not a unique miracle of Earth, but a common phenomenon in the cosmos. This knowledge would completely reshape our understanding of biology itself. To secure this incredible opportunity, a permanent research station would need to be established below the ice, anchored to the underside of the crust. This habitat, a pressurized bubble of light and warmth in an eternal, sunless ocean, would be a monument to human curiosity and remote engineering. The scientists and engineers living there would face profound isolation, communicating with Earth through a time-delayed link that takes hours to travel across the vast gulf of space. Their work would be slow and meticulous, governed by the highest principles of planetary protection to ensure we do not contaminate this pristine environment with our own microbes. The ethical questions are as deep as the ocean they study. If we find life, do we merely observe or do we interact? How do we approach a second genesis of biology with the respect it deserves? A confirmed discovery on Europa would force us to reconsider our entire approach to space colonization, shifting from a model of pure conquest to one of careful, reverent exploration. It would teach us that some worlds are not meant to be settled, but to be understood as sanctuaries of nature, each holding unique chapters in the story of the universe. Far from the sun's warmth, beneath the hazy orange sky of Saturn's moon Titan, lies a resource that could power an entire civilization. This is not a world of rock and ice alone, but one graced with vast lakes and rivers flowing with liquid methane and ethane. A colony here would pioneer a truly alien economy, built not on water but on hydrocarbons. These lakes would be more than a curiosity. They would be the lifeblood of the settlement, pumped directly into refineries to be cracked and reformed into the building blocks of industry. The methane would become rocket fuel for shuttles, raw material for manufacturing durable plastics, and a base for creating fertilizers to support food production within sealed biospheres. This self-sufficient cycle turns Titan's greatest abundance into a complete economic engine, one that operates independently of shipments from Earth. To survive on the surface where temperatures plunge to -180 degrees Celsius, habitats would be constructed under massive, heated domes. These pressurized enclosures would shield inhabitants from the extreme cold and the thick, nitrogen-rich atmosphere, creating pockets of Earth like warmth in the deep freeze. Transportation between these outposts would take to the skies, utilizing the moon's low gravity and dense air. Helium-filled balloons could carry cargo with ease, while autonomous drones would zip through the orange haze, surveying the landscape and connecting the network of domes. This project is a masterclass in radical adaptation. It proves that a colony's success hinges on its ability to read the local environment and utilize exactly what it finds, rather than trying to recreate Earth exactly. The settlers on Titan would become experts in a chemistry that is exotic to us, building a society that breathes hydrocarbons as naturally as we breathe air. This approach of living within an alien system rather than fighting it could become the standard model for thriving on the most unexpected worlds throughout the galaxy. Our civilization now has power, resources, and homes, but a society spanning such vast distances faces a fundamental challenge: the speed of light. Radio signals take minutes to reach Mars and hours to travel to the outer planets, creating a lag that could cripple coordination and fray social bonds. The solution lies in the strange and counterintuitive world of quantum physics, specifically a phenomenon known as entanglement. This is the foundation for a solar system-wide quantum communication network, an internet for the stars where information travels instantaneously. Imagine two particles linked in such a way that whatever happens to one immediately influences the other, no matter if they are sitting in the same lab or are separated by the gulf between Saturn and Earth. By carefully manipulating these entangled pairs, we could create a channel for sending data that is not only faster than light, but fundamentally secure. Any attempt to eavesdrop on this quantum link would disturb the delicate state of the particles, instantly alerting both the sender and receiver to the intrusion. To build this network across the solar system, we would need to place a constellation of specialized satellites at strategic points. These quantum repeater stations would act like signal boosters, generating fresh entangled particles and passing the connection along, creating a web of instant communication linking Earth, Mars, the cloud cities of Venus, and the research outposts on the moons of Jupiter. This real-time data flow is the nervous system of our interplanetary civilization. It allows a pilot in the asteroid belt to navigate through a dense field of rocks with live sensor data from a dozen different satellites. It lets a family on an O'Neill cylinder have a perfectly clear video call with relatives back on Earth without any frustrating delay. For governance and collective security, this network is indispensable, ensuring that every part of human space is always on the same page, able to respond to emergencies or coordinate massive projects as a single, unified entity. This quantum web turns a collection of isolated outposts into a truly connected society. Yet, a society that feels secure in its connections must also be able to protect the very infrastructure that makes its existence possible. A civilization that spans worlds must also be prepared to defend them. The void is not entirely empty, but filled with ancient remnants from the solar system's formation, some of which cross our path. The planetary defense grid is our collective shield, a unified network of vigilant eyes and capable hands. Its first layer is an ever-watchful array of telescopes, stationed from the orbit of Mercury to the distant Kuiper belt, constantly scanning the darkness for any object on a potential collision course with an inhabited world. Early detection is everything, providing the precious time needed to mount a response. When a threat is identified, the grid's second layer activates. This is not about destruction, but about precision. A kinetic impactor, essentially a massive projectile, could be sent on an intercept course to deliver a gentle push, just enough to alter the object's trajectory over millions of kilometers. For larger bodies, a gravity tractor would be deployed, a spacecraft that would fly alongside the asteroid for years, using its own minuscule gravitational pull to slowly and safely tug it off course. In more urgent scenarios, arrays of mirrors could focus the sun's light into a powerful laser, vaporizing a portion of the rock's surface and creating a natural jet of gas that acts as a thruster. This system transforms a random cosmic hazard into a managed, calculable risk. It represents a fundamental shift in our relationship with the universe, from passive inhabitants to active stewards of our shared space. The grid is a testament to a civilization that has chosen to protect all its homes, from the domed cities of Mars to the floating archipelagos of Venus. This hard-won security provides the stable foundation for our most monumental undertakings, allowing us to focus on creation rather than mere survival. With our safety assured, we can turn our attention to a project that stitches our scattered colonies together with threads of light and data. A thin ribbon of pure carbon descends from the sky, connecting the rust-red surface of Mars directly to its captured moon. The Phobos space elevator is an engineering marvel that turns a celestial coincidence into the most efficient transit system imaginable. Mars's moon, Phobos, is tidally locked, meaning the same face always points toward the planet, and its orbit is so low that a cable anchored to its surface could dangle all the way down into the Martian atmosphere. This is not a static structure, but a dynamic one, with the entire moon acting as a counterweight at the end of a carbon nanotube tether thousands of kilometers long. Electrically powered climbers, like high-speed elevators, would glide up and down this ribbon, carrying massive loads of cargo and passengers between the surface and orbit. The energy required is a fraction of what is needed to launch a traditional rocket, effectively turning the immense challenge of escaping a planet's gravity into a simple, scheduled commute. This single innovation would slash the cost of building a new world. Imagine the steady stream of equipment it could deliver: massive drills for subsurface aquifers, entire greenhouse modules for early settlements, and the industrial reactors needed for the next phase of terraforming. It transforms the daunting prospect of supplying a civilization from a series of heroic, expensive launches into a routine and continuous flow. This elegant solution demonstrates a profound principle that the key to thriving in space often lies not in fighting physics, but in understanding and leveraging its subtle harmonies. With such a reliable conduit established, our ambitions can shift from mere access to truly permanent, foundational change. The Moon's surface holds a secret architecture, a network of caverns left behind by ancient rivers of fire. These colossal lava tubes form the perfect foundation for a subterranean metropolis, a city shielded from the harsh realities of the lunar environment. Its ceiling is a solid roof of rock meters thick, a natural barrier against cosmic radiation, the constant barrage of micrometeorites, and the wild temperature swings between blistering day and frigid night. Within these vast, hollowed-out spaces, the real work of engineering begins. Instead of building massive domes from scratch, we would simply seal the ends of the tubes and fill them with a breathable, pressurized atmosphere. This creates an immense, ready-made volume for living, a cavern so large it could contain entire city districts under a single, stable arch of basalt. This lunar city would quickly become a center of intense activity, a hub for mining the rare helium-3 embedded in the soil for future fusion reactors, for astronomical observatories placed on the far side in perfect radio silence, and as a crucial refueling station. The water ice confirmed to exist in permanently shadowed craters at the poles would be the settlement's lifeblood, split into oxygen for breathing and hydrogen for powering the rockets that launch from here to Mars and beyond. This project demonstrates a profound shift in our approach to living in space. It is not about conquering a landscape, but about listening to it and using the gifts it offers. The lunar metropolis is a lesson in cosmic humility, showing that the most elegant engineering often works with a world's natural geometry, not against it. While this city thrives in a ready-made cave, our next ambition requires the opposite approach, forging entirely new land where none existed before. A rotating ring becomes the beating heart of a space station, a simple yet profound solution to one of our greatest physiological challenges. This artificial gravity ring spins steadily, using centrifugal force to create a familiar downward pull. Inside, the environment feels entirely normal. You could walk across a grassy park, feel the weight of your body as you exercise, or watch water flow downwards from a tap, just as it does on Earth. This is not a luxury, but a medical necessity for any long-term settlement. The human body evolved for gravity. Without its constant pull, our bones begin to leach minerals into the bloodstream, becoming dangerously brittle over time. Our muscles, no longer fighting gravity to hold us upright, weaken and atrophy. An artificial gravity ring directly counters this decay, providing the constant stimulus our bodies need to stay healthy. This section of the station would be dedicated to life itself, housing spacious living quarters, fully equipped gyms for maintaining strength, and lush hydroponic gardens that provide fresh food and a vital psychological connection to a living world. It offers a crucial refuge, a slice of Earth normalcy amidst the alien reality of zero gravity. This innovation transforms the very definition of living in space. It shifts the goal from mere survival to true sustainability, making it possible for people to raise families and build communities without sacrificing their long-term health. A civilization that has mastered artificial gravity is one ready to undertake its most ambitious journey yet, a multi-generational voyage to another star. A self-contained world sets sail into the endless night. This is the generation ship, a civilization in miniature embarking on a voyage lasting centuries. Its destination is a nearby star like Proxima Centauri, but its true purpose is to carry the flame of humanity itself. The vessel is a technological cathedral, incorporating every system we have explored. Its massive hull, built in the orbital shipyards, spins to provide artificial gravity for the generations born within. Its closed ecological system, more advanced than any Ceres Arcology, meticulously recycles every drop of water and molecule of air, supporting vast internal farms that feed thousands. Propulsion could come from sustained nuclear fusion, a controlled star pushing the ship ever forward, or from immense light sails, kilometers wide, catching the momentum of laser beams fired from our own solar system. But the greatest challenge is not engineering, it is society. The crew that departs will not be the one that arrives. Their children and their children's children will be the ones to finally see the new sun rise. This creates a culture entirely dedicated to the mission, where every individual understands their role in a story larger than a single lifetime. Education, history, and technical skills become the core of their identity, passed down with the solemn duty of shepherds. This project is the ultimate test of our resilience, a guarantee that even if catastrophe strikes our home system, a fragment of humanity will endure among the stars. To sustain such a journey, the ship's life support must be flawless, a perfect mechanical biosphere that can function without any outside help for 1,000 years. A truly independent civilization requires a living, breathing heart that beats on its own. These are the closed-loop biospheres, engineered worlds where every molecule of air and every drop of water is in constant, purposeful motion. Within their transparent domes or sealed hulls, a delicate dance unfolds. Plants absorb the carbon dioxide we exhale and, powered by artificial sunlight, transform it into fresh oxygen and food. Specialized microbes break down our waste, purifying water and replenishing the nutrients in the soil that feeds the plants. It is a perfect circle of life, meticulously designed to function without any outside input, a tiny, self-sustaining piece of Earth that can be placed anywhere in the cosmos. This is far more than a life support system. It is the very definition of a permanent home. The monumental challenge lies in achieving perfect stability. Early experiments like Biosphere 2 taught us hard lessons about the unpredictable nature of sealing an ecosystem. Unforeseen drops in oxygen and explosions in certain insect populations revealed just how complex and interconnected these systems truly are. We learned that a closed loop is not a static box, but a dynamic, living entity that requires constant, subtle management. Mastering this balance is the final step in cutting the umbilical cord to our home planet. A habitat that can maintain its own air, water, and food for generations is no longer an outpost, it is a sovereign world. This hard-won biological independence provides the ultimate security, freeing us to pursue our most profound questions in places where no life was ever meant to be. The ultimate telescope would not be built by human hands, but by the fundamental geometry of space-time. Beyond the orbit of Pluto, far past the scattered icy bodies of the Kuiper belt, lies a point of perfect cosmic focus. At a distance of 550 astronomical units, the Sun's gravity bends the light from distant objects behind it into a brilliant, magnified ring. By placing a spacecraft at this precise location, we could transform our star into a gravitational lens, creating an observatory with capabilities that dwarf any instrument we have ever conceived. This solar gravitational lens telescope, a vision advanced by researchers like Slava Turyshev at the Jet Propulsion Laboratory, would not merely see exoplanets as faint dots of light. It would resolve them, Imagine directing this immense natural instrument toward a promising world like Proxima Centauri b. The data streaming back would not be a blurry spectrum but a detailed image. We could map the outlines of continents and deep blue oceans against its surface. We might trace the reflective glint of polar ice caps, or even detect the faint, organized glow of city lights on its night side, a potential signature of a civilization not our own. The journey to this focal point is a monumental undertaking in itself. A probe would need advanced propulsion, perhaps a massive light sail pushed by powerful lasers, to reach a destination so remote that a radio signal would take weeks to make the one-way trip. The spacecraft would spend decades in the silent dark, a lonely sentinel on a pilgrimage for a glimpse of another Earth. Upon arrival, its work would be meticulous and slow, requiring it to carefully maneuver to align the Sun with a specific target star, then spend years collecting the infinitesimally faint photons that form the Einstein ring around our star. The data returned would answer one of humanity's oldest questions. Are we alone? But it would do more than that. It would tell us what kind of universe we live in, one teeming with life and activity, or one where living worlds are rare and precious jewels. This quest for knowledge pushes the very boundaries of observation, forcing us to develop the technologies for long-duration, autonomous missions across unprecedented distances. The same determination that drives us to see across the light years will ultimately be the force that carries us there, inspiring us to push the boundaries of habitation as well. The surface of Mercury faces a perpetual, scorching day, a landscape bathed in unfiltered solar fury. Here, the Sun appears 3 times larger than it does from Earth, delivering a constant, overwhelming flood of energy. This makes Mercury the ideal location for the solar system's ultimate power plant. Vast fields of advanced solar panels would cover entire regions of the planet, each cell engineered to withstand the extreme temperatures and convert the intense light into electricity with staggering efficiency. This raw power would then be fed into colossal transmission arrays, structures that rise from the barren rock like silent, technological monuments. Their purpose is to convert this captured sunlight into a tightly focused beam, either of microwaves or laser light, and aim it with perfect precision across the void. Their targets would be receiving stations millions of kilometers away, perhaps in orbit around a cloud city at Venus, or a domed settlement on Mars, or even a research outpost on a moon of Jupiter. This is the Mercury Solar Power Relay, a megaproject that transforms the innermost planet from a barren world into a specialized hub for the entire civilization. It represents a profound shift in how we view our place in the solar system. Instead of every colony struggling to generate its own power from limited local sources, we begin to think as a single, interconnected entity. Mercury, with its unique and extreme environment, takes on the vital role of energy producer. This systemic approach to resource allocation is the key to a truly sustainable interplanetary society, where each world contributes what it does best for the benefit of all. It is a lesson in cosmic economics, proving that cooperation across millions of kilometers is not just possible, but essential for our future. This grand, unified vision of a civilization working in perfect harmony sets the stage for the final and most integrative project of all. This final megaproject is not a structure of metal and glass, but a web of pure intelligence. A decentralized administrative artificial intelligence would act as the silent, central nervous system for our entire civilization among the stars. Think of the sheer complexity it would manage, a constant flow of ships navigating the interplanetary transport network, the delicate scheduling of resource deliveries from the asteroid belt, and the real-time energy distribution from the Mercury solar relay to a thirsty outpost on Mars. This system would not issue commands, but rather offer a constant stream of optimized suggestions, predicting bottlenecks before they form and rerouting cargo to avoid a potential collision by a fraction of a degree. It is the ultimate tool for coordination on a scale too vast for any human committee to comprehend. By analyzing petabytes of data from every sensor, every habitat, and every ship, it could balance the entire solar system's economy, ensuring that a shortage of rare minerals on a Jovian moon is met with a supply from the belt before anyone even realizes there is a problem. This artificial intelligence would be the great harmonizer, the force that allows 20 independent, colossal megaprojects to function as a single, resilient organism. Its core programming would be one of service, designed from the outset to augment human oversight, not replace it. The most critical decisions about the pace of terraforming, the ethics of exploring European oceans, or the cultural direction of a generation ship would always remain in human hands. This system simply provides the clarity and foresight needed to make those choices with wisdom. It is the culmination of all our ambitions, the cognitive framework that turns a collection of spectacular achievements into a unified, enduring civilization. Having journeyed through these 20 pillars of a new society, we are left with a profound question. What does it mean to be human when our home is no longer a single planet, but an entire solar system? These projects are not just about survival, they are a declaration of our potential, a blueprint for a future where humanity becomes a multi-world species, forever changed by the stars we now call home. This tapestry of 20 megaprojects paints a future not of isolated achievements, but of a deeply interconnected existence. We have moved beyond the question of whether we can build these structures to a more profound inquiry. What kind of civilization will we become by building them? Each endeavor, from the terraformed plains of Mars to the silent intelligence guiding our economy, is a single instrument in a grand cosmic orchestra. Their true power is revealed not in isolation, but in their synergy, creating a society of unimaginable resilience. A solar flare that disrupts power on one world can be compensated by the Mercury relay. A crop failure in a Ceres Arcology can be met with shipments from an O'Neill Cylinders farms. This distributed network ensures that no single point of failure can threaten the whole of humanity ever again. Our identity will inevitably evolve as we spread across the solar system. The children born in the floating cities of Venus will grow up under a yellow sky, their concept of home fundamentally different from those who tend the hydroponic gardens of a lunar metropolis. New cultures, new art, and new philosophies will blossom in these alien environments, each one a unique branch of the human story. This diversity is our greatest strength, a testament to our ability to adapt and find meaning wherever we go. The journey to this future demands a new kind of collaboration, one that transcends the terrestrial borders that have so often defined our history. Building a Dyson Swarm or a planetary defense grid requires the shared resources and intellect of our entire species, a unified purpose that can turn competition into common cause. It asks us to make peace with timescales that dwarf individual lifetimes, investing in cathedrals whose domes we will never see completed, for the benefit of generations we will never meet. This is the ultimate legacy of these 20 visions. They are not just blueprints for engineering, but a mirror held up to our own potential. They challenge us to be wiser stewards, more daring explorers, and better ancestors to those who will one day call the stars their home. This grand tapestry of 20 megaprojects paints a future not of isolated achievements, but of a deeply interconnected existence. We have moved beyond the question of whether we can build these structures to a more profound inquiry. What kind of civilization will we become by building them? Each endeavor, from the terraformed plains of Mars to the silent intelligence guiding our economy, is a single instrument in a grand cosmic orchestra. Their true power is revealed not in isolation, but in their synergy, creating a society of unimaginable resilience. A solar flare that disrupts power on one world can be compensated by the Mercury relay. A crop failure in a Ceres Arcology can be met with shipments from an O'Neill Cylinders farms. This distributed network ensures that no single point of failure can threaten the whole of humanity ever again. Our identity will inevitably evolve as we spread across the solar system. The children born in the floating cities of Venus will grow up under a yellow sky, their concept of home fundamentally different from those who tend the hydroponic gardens of a lunar metropolis. New cultures, new art, and new philosophies will blossom in these alien environments, each one a unique branch of the human story. This diversity is our greatest strength, a testament to our ability to adapt and find meaning wherever we go. The journey to this future demands a new kind of collaboration, one that transcends the terrestrial borders that have so often defined our history. Building a Dyson Swarm or a planetary defense grid requires the shared resources and intellect of our entire species, a unified purpose that can turn competition into common cause. It asks us to make peace with timescales that dwarf individual lifetimes, investing in cathedrals whose domes we will never see completed, for the benefit of generations we will never meet. This is the ultimate legacy of these 20 visions. They are not just blueprints for engineering, but a mirror held up to our own potential. They challenge us to be wiser stewards, more daring explorers, and better ancestors to those who will one day call the stars their home. The first step to building among the stars is to believe it is possible. If this vision of the future excites you, subscribe for more deep dives into tomorrow's technology, and let us know in the comments which megaproject you would want to see become a reality first.